Good morning, good evening, or good afternoon, Bearcats. All right, this is 9.5 Binomial Theorem. We're going to learn today, or what you should learn, is you're going to learn about the Binomial Theorem, which is used to calculate binomial coefficients. You're going to learn to use Pascal's Triangle to calculate binomial coefficients. And you're going to learn to use binomial coefficients to write binomial expansions. So, these are all the key things that you're going to learn from this lesson. Just a reminder, a coefficient is the value or the number before the variables in an expanded polynomial. Remember from the past, this is the things that we know. A binomial is a polynomial that has two terms. So in other words, a binomial has two terms. So x plus y. And if we have it expanded, we could have x plus y to the 0, to the first, to the second, to the third, etc. We're going to talk a little bit about what we already know about these binomials and then what we can learn that will help us in our expansion. Let's move on. Go Bearcats. Okay, these are some of the things that we already know about binomials. One of the things that we've learned and used a lot this year is a binomial squared. When we have a binomial squared, let's say x minus 3 squared. We've learned a shortcut that we've used all year, and that's a really, really important shortcut, so let's take a look at that. We would take the first term x and we would square it. We can multiply through all three terms, x times negative 3 times 2, and get negative 6x, and then plus 9. And that was a shortcut to FOILing. If we had FOILed, it would have been x minus 3 times x minus 3. We would have x times x is x squared, x times negative 3, negative 3x, negative 3 times x, negative 3x, and finally negative 3 times negative 3 would have been a positive 9. We would have combined like terms and gotten the same result. So x squared minus 6x plus 9. This allowed us to be, was a shortcut. And really, that's what we're going to talk about today, are some shortcuts. Imagine if we were asked to do x minus 3 to the 7th, or to the 107th. Hopefully we wouldn't have to do that. It would take a long time. But here's what it would look like. I don't have a shortcut that we know of yet, but we're going to learn one today. But with what we know already, we would multiply this out and FOIL it. So we'd have x minus 3 times 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 x minus 3. 1, 2, 3, 4, 5, 6, one more, x minus 3. All right, well, we already know because we did the shortcut. When we square them, we would have gotten x squared minus 6x plus 9. If we squared these two, we've gotten x squared minus 6x plus 9. These two, x squared minus 6x plus 9. And this one would have been by itself. And we would have had to continue, and you can imagine how long this would take us. Not something that we really want to do. So let's take a look at the root of binomial expansion, and then the shortcuts we're going to use to expand an example like this. And we'll actually do this example in a few minutes. So you may want to write down your shortcut if you don't remember it, and then just pause as long as you need and write down the information that you need. All right, let's just take a look at basic expansion. One thing I want us to note is the power listed here for what we're doing today. This power that we see, that is going to be our n value, So let's take a look at this just basic expansion, and then we're going to take a look at two specific ways to get our coefficients. All right, in this term, in this x and y would be, x is going to represent the first term of your binomial. Y will represent the second term of your binomial. So it doesn't mean that everything is going to always be x and y. X could be 2x or 3x, and y, and it could be 2a or 2b. It doesn't have to be the x is the variable. But in this format, we're recognizing that that represents whatever the first term is in our binomial, and y the second term. So if we raise it to the 0 power, anything to the 0 power is 1. Remember that in a few minutes, because we're going to do several things where you realize that 1 becomes a very, very powerful number. All right, in the second term, x plus y to the first, anything to the first power be itself, we would just have x plus y. And actually, you'd have 1x plus 1y. Let's take a look at that. Remember I said 1 is a very powerful number. If we binomial squared, remember we have the shortcut, we square the first term, so I'm going to say 1x squared, multiply, you get plus 1 times 1 times 2, which would just be 2xy, and then we would have y squared, which would be plus 1y squared. Notice the ones, the 1, the 1, the 1, the 1, the 1. And then there's some different things in the middle. All right, let's go to the cube. I'm just going to write this out, and I want you to start to recognize the pattern that you're seeing. The pattern that you're seeing. So I'm going to say this would be 1x cubed plus 3x squared y to the first plus 3x y squared, and we'll say x to the first, plus 1y cubed. Okay, notice a couple of things here. The coefficients increase and then decrease. So we go 1, 3, 3, 1. The exponents, notice something about the exponents. The exponents, if you add the exponents together, they're going to equal the power. So this is just a 3 and this is a 3. If you add the 2 and the 1, you get a 3. The 1 and the 2 and you get a 3 and a 3. That's a very strong pattern that we're going to notice in this. Also notice that the powers increase and decrease on your x and y. So as x will increase, you have, or decrease, x to the third, x squared, x to the second, and then basically x to the 0. And then you have y to the 0, y to the first, y to the second, y to the third. So the first term increases its exponent starting with the highest degree, and then the second term will, decreases on the first term. Second term will increase starting with, you start with the 0 power and you increase to the highest degree of the binomial. Alright, so let me go ahead and continue to show you, and then we'll look at some other properties that you're going to notice. And we're going to see these properties again in a few minutes in something else that we're doing. Alright, so this one would be 1x to the fourth. If you need to pause and write this down, I would have this example in my notes. 1x to the fourth plus 4x cubed y to the first plus 6x squared y to the second plus 4xy cubed plus y to 1y to the fourth. Again, let's take a look at that symmetry. We have 1, 4, 6, 4, 1 goes up and then back down for the coefficients. Our exponents on the first term, x to the fourth, x to the third, x squared, x to the first, x to the 0. Our coefficients on the second term, y to the 0, y to the first, y to the second, y to the third, y to the fourth. It's increasing. Very, very, very symmetrical. The sum of the powers, this is 4, 3 plus 1 is 4, 2 plus 2 is 4, 3 plus 1 is 4, 4 is 4. Notice that. One thing we haven't talked about is that the number of terms. The number of terms is one more than the given exponent, than the given power. So if this is to the 0 power, we have one term. Remember I said 1 was important. We have the first power, we have 2 terms. The second power, 3 terms. The third power, 4. The fourth power, 5. So the number of terms is going to be n, which is our power, plus 1 each time. And I think that covers all of our symmetry and pattern. Let's go ahead and take a look at the fifth expansion, and let's see if you can kind of guess. Matter of fact, I'm just going to let you pause for a minute and let you fill it in. So why don't you pause and see if you can do that on your own, and then I'll be waiting right here for you, and you can come back and check your answer with me. Okay, hopefully you filled it in. Go ahead and check your answer with mine. So of course the first term is 1. We like that 1 coefficient. And notice we begin and end with 1 in every single case in our expansion. So if you decide to drop the 1, then there would be no coefficient in front, but the understood coefficient would be 1. And we know we would start with the first term to the highest power, so we'd have x to the 5th. So the next term would be plus, and we would have 5. Notice that the second term coefficient is always the same as the coefficient of the power. Now that's not going to be true as we go along and we have numbers in our x and our y values change. If that's 2y, then that's going to change the coefficient. But if it's just an x and a y, then that would be true. So just make sure you don't see that pattern and think it's always going to be 5. If y has a variable or x has a variable or coefficient in front of it, then that will change those values. And we're going to look at how we find the coefficients in just a minute. But the one thing that won't change is the coefficients should increase and then usually decrease. All right, so we have x to the fourth and y to the first plus 10x cubed y squared. Notice the x values powers are decreasing, the y value powers are increasing. Then we would have 10 again, and we would have x squared and y cubed. And then we would have 5 again, and we would have x and y to the fourth, and then finally we would have y to the fifth. And this pattern would continue. One more time, we're going to recap the symmetry and the patterns that we see here. Let's talk first about the expression, the number of terms. So if we have a zero power, if we have one term, two terms, three terms, etc. So the number of terms is one more than the power. So it's the power plus 1. The power plus 1. You'll remember earlier in the year the number of turns, T-U-R-N-S, the number of turns in a polynomial was always 1 less the power. So the power minus 1. So just some interesting trivia here for you. All right, next, the x and y have a symmetrical role. So in other words, that the powers of x decrease as the powers of y increase. And the sum of the powers in each term totals the power given in the original binomial. The coefficients increase and then they decrease, and these are called binomial coefficients. All right, let's learn a little bit more about the specifics of those coefficients. All right, let's talk a little bit about the binomial theorem. And this is something that you will have to know for your assessment. You will have to know this. I'm not going to have it written down anywhere for you. You do need to know this. The binomial theorem is used to find the coefficients in a binomial expansion. In other words, those numbers in front of each term in our expansion. It's written a couple of different ways. One, you'll see it as C and then sub n r. And we've done this a little bit before. This has to do with factorials. Sometimes you may see it written just in r with a parenthesis, so it can be written in either form, but it is equal to n factorial over n minus r factorial times r factorial. And we did factorials last week, so that you should be familiar with. I do want to talk a little bit about what the n and the r represent. What the n and the r represent. We've already discussed n in the previous little discussion, and that is the power of the binomial. So that's the power of the binomial, or the expansion number, how many expansions we want. So if it is x plus y to the 8th, then we want 8 expansion, and we expand it to the 8th expansion, or the power of 8. The r is the term number. But remember, we must remember, or must know, that the first term is called the zero term, is a zero term. So in other words, if it's physically the fifth term, then it's really r to the 6th, because the first term was 0. We looked a little bit at that when we talked about sequence and series, whether they started at your lower starting point was at 0 or 1. It made a difference, and we're going to start at 0. So the r will be one more greater than actually the term number that you're looking for. So anyway, we just have to take a look at that. All right, so another way to write this. Okay, so let's look at an example. All right, let's look at this example. We have C sub A 2. All right, so, or it could be written as 8 2. This would be the first term because the term number is 2. So the physically it'd be the second term in the expansion, because it would be term 0, 1, 2, 3, 4, etc. This would be term 0, this would be term 1, this would be term 2. So technically term 2 would be the third one. Let me say that a little differently. I think I've kind of confused U. So this is term 0, term 1, term 2, term 3. So technically this is physically this is the first term, the second term. So we're really looking for term 1, or the first term in our binomial expansion. That's kind of confusing. As we move on, I think that'll make a little more sense. You just have to remember that everything starts at 0. Everything starts at 0. So let's take a look at how we would plug this in. If we're just using the binomial theorem and we already have it written this way, it's pretty easy. We would say 8 factorial. We would have 8 minus 2 factorial, and then 2 factorial. And just to review how we would handle our factorials, that would be 8 times 7 times 6 times 5, etc. Okay, that would go on and on and on. I'm just going to put factorial at the end. You'll see why. 8 minus 2 is 6 factorial and 2 factorial. We can go ahead and cross out our 6 factorials because we know that's 6, 5, 4, 3, 2, 1 both ways. We could make that cancellation. 2 factorial, we would have 8 times 7 left at the top, and that'd be 2 times 1 at the bottom. The 1 you may or may not need, but let's go ahead and write it. Then we can just do basic cancellations. 2 goes into 8 4 times, 1 goes into 7 7 times, 4 times 7 is 28. So this term number right here would have a coefficient of 28. So that's just an example. Now I want you to try, and I want you to highlight, listen carefully, I want you to highlight this in your notes. So when I come by tomorrow to help you, I can look at your notes and make sure that you have taken these down and that you worked on your video. So here we go. I want you to try C sub 10, 3, or it can be written as 10, 3, and I want you to get me an answer. So I want you to highlight this problem right here. I want you to show me the work, and then I want you to circle and highlight your answer. So I should see a big highlighted area. If for some reason you don't have a highlighter, then find a different color and circle it and make it sure that when I come by I can see it really well. Alright, let's move on. Go Bearcats! Alright, next I want to take a look back at this expansion, this x plus y to the 5th power, and this would be our expansion. I want us just to extract those coefficients. So our coefficients are 1, 5, 10, 10, 5, 1. So I'm going to circle them. And we've already talked about the symmetry and the pattern in this. I wanted you to know that there's a very convenient way to remember this pattern for binomial coefficients. It's called Pascal's Triangle, and it will just show you the great symmetry of binomials. So I'm going to show you that pattern right now. So you're going to want to, when I move to the next screen, you're going to want to pause and you're going to want to write this information down in your notes. You're going to want to have this down. So I want you to pause and I want you to write both of these things down, and then we're going to discuss them. But I really need you to have them written down before we talk about them so that I can make the comparison and you can recognize the great pattern here. Okay, hopefully you're back. Go Bearcats! Alright, so I want you to notice a couple of things. Notice this Pascal's triangle. Notice how we generate the numbers below. Remember I told you the power of 1. Well, remember this is really x plus y to the 0 power is 1. That's where the 1 came from. And to the first we would have x, 1x and 1y, so 1 and 1 would be our coefficients. Alright, notice that the coefficients over here are the same as in the triangle. The triangle is generated very easily. So you're going to say, always start with 1, and then you have these two numbers which give you 2, and then you end with 1. You start with 1. These two numbers give you 3, these two numbers give you 3, and then you have 1. You start with 1. 1 and 3 give you 4, 3 and 3 give you 6, 3 and 1 give you 4, you end with 1. Start with 1. 1 and 4, 5, 4 and 6, 10, 4 and 6, 10, 4 and 1, 5, 1. Etc. So the generation of this triangle is very easily. We're just basically adding the two numbers above it to get the results. So it's a pretty easy thing, and it does lead us to our coefficients for our binomial expansion. Remember a couple of things. The top row is called the 0th row. Alright, it's called the 0 row because it's x plus y to the 0 power. Also, in the term numbers, remember we said that the term numbers is one more than the r. So the power is always this second term. So this is really an x plus y to the 7th power. And we have 1, 2, 3, 4, 5, 6, 7, 8 terms, because the first term is the 0 term. So this is the 0 term, the first term, the second, the third, the fourth. So when I'm asking you to find the second term, it's the second in the expansion, which is technically the first if you counted from 0. A little confusing. It'll get easier as you practice with that. Let's take a look at some examples. All right, let's take a look at this example. The x is going to be our x value, and the 2 will be like our y value, and we are expanding to the fourth expansion of the power of 4. So we need the fourth row of our Pascal triangle. And remember, the top row is 0. So 0, 1, 2, 3, 4. We'll be using this row of Pascal's triangle. So let's go ahead and just create that really quickly. That would be 1, and it would be 1 and 1. It would be 1, 1 plus 1 is 2, and 1. It'd be 1, 1 and 2 is 3, 2 and 1 is 3, 1. And it would be 1, 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4 and 1. And you know it's the fourth row because of the 4 right there. So that's an easy way to remember. So you just start your pattern and look for that second number to give you your power. All right, these will be the coefficients in front of our terms. So we're going to have to be really careful in front of our terms. So I'm going to kind of spread those out. Now there are multiple ways to do this, and look at this and multiply these out, and I'm fine with whatever method works best for you. This is how I do it because I think it works really well. Since this is a plus, we don't have to worry about the alternating signs, so we're just going to start with our coefficient. So we have a 1, and then we know we're going to add to that in a minute something with a 4, and something with a 6, and something with a 4, and then something with a 1. And those are the coefficients. I'm just going to circle those to begin with. And then we're going to do our first term, and our first term happens to be x. And so we know x will be descending, so we start with x to the 4th. So this is going to be x to the 4th, and then it's going to be x cubed, and it's going to be x squared, it's going to be x to the 1st, and then it's not going to, x to the 0 is just 1. And then we're going to start with our second term, which is our represented by y in our formula, but in this case, our second term is 2. All right, so it's going to be 2 to the 0, and I'm going to go ahead and write that in so you understand what that was. Then it's going to be 2 to the 1st, 2 to the 2nd, 2 to the 3rd, and 2 to the 4th. All right, and so I'm going to put all these kind of in parentheses just to keep them all straight. And we'll put addition signs in between each of these, and we're ready to go to tabulate everything. All right, well, 2 to the 0 is 1. So we have 1 times x to the 4th, so we have x to the 4th. Plus, now, we have 4, we have x cubed, and we have 2 to the 1st. 2 to the 1st is 2. So 2 times 4 is 8. So we will have 8x cubed. Notice what's happening. Then we're going to have a plus sign. We have 6. We have x squared, and we have 2 squared. 2 squared is 4. 4 times 6 is 24x squared. The next term, plus, we have 4, we have x to the 1st, and we have 2 to the 3rd. 2 to the 3rd is 8. So 4 times 8 is 32x. And then finally, we have 1, and 2 to the 4th is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. 1 times 16 is positive 16. Okay, notice, even though it wasn't as symmetrical as our original triangle because we changed the value of y to a number, it's still moving up and then going back down. So the coefficients are 1, and then they go upward, and then they move back and get smaller. So you will still see that type of pattern. All right, let's maybe take a look at one more example. All right, I actually am going to give you a few minutes. I really think if you understood the last example, I think you should try this one on your own. So what I'd really like for you to do is write this one down and pause the video and go ahead and work it out, and then take a look at my work. So I'm going to let you do that on your own. If you choose not to do that, you need a little more explanation, you go ahead and watch me work through it. But I would suggest you stop right now and go ahead and try to work it yourself, and then just check your work. I will go on and go ahead and work it, but if you want to do it on your own, pause right now, and I'll be waiting for you. Okay, for those of us who are going to go on together, we're going to go ahead and create Pascal's Triangle to row 4. I'm not even going to think about what row numbers. I'm just going to start with, I know it starts with 1. I know 1, 1. I know 1, 2, 1. I know 1. 1 and 2 is 3. 2 and 1 is 3, 1. I know 1. 3 and 1 is 4. 3 and 3 is 6. 3 and 1 is 4 and 1. And I'm going to stop because I'm looking at that second term, and the second term, which is technically my first term because it's a 0 term, remember, is 4, and I know that I'm at the right level of my Pascal's triangle. Because this is subtraction, we're going to start with subtraction, and we're going to alternate the signs, negative, positive, etc. in our form. So that's kind of important. The next thing I'm going to do is we're going to put the coefficients down. These are the coefficients for that come in front of your other x and y terms. So we're going to go ahead and write those down. I'm going to have a 1. I'm going to circle it. I'm going to skip some space, and I have a 4. I'm going to circle it. I'm going to skip some space. I have a 6. Then I'm going to have a 4. And then I'm going to have a 1. So those are the coefficients. Those come straight out of the triangle. Next, I'm going to take my first term, which is 3x. I'm going to write it down each time. And this is just the pattern I use. You can do term by term by term. I'm fine with that. Whatever works best for you. Remember our first term, whatever our first term is, we're going to start with the power and then descend. So this will be to the 4th power, the 3rd power, the 2nd power, the 1st power, and of course the 0 power. And you know that. You could have just created a 1 there immediately if that works for you. But I just want to demonstrate how this works. The next term is going to be our y value. So I'm going to put a y, a y, a y, a y, and a y. And this one works in reverse. We start with the 0 power, and then we have the 1st power, the 2nd power, the 3rd power, and the 4th power. And then you want to make sure that, just to check yourself, that the powers add up to 4. 4 and 0, 4. 3 and 1, 4. 2 and 2, 4. 1 and 3, 4. 0 and 4, 4. So they do. And again, I said because of this subtraction sign, we're going to start with subtraction, and we'll have addition, subtraction, addition. And that's how that works. That's not too bad. Now it really does become just nitty-gritty cleanup time. Nitty-gritty cleanup time. So we have a 1. Be careful. We have 3 to the 4th power. 3 to the 4th power is 81x to the 4th. And then y to the 0 power is just 1. So we have, I'm going to go ahead and do these terms as I go. So we have 1 times 1 is 1 times 81. So we have 81x to the 4th. So like I said, it doesn't always mean in a binomial expansion that your first term or your 0 term is going to start with a 1. It just means that the coefficient was a 1. If your x and y's have coefficients themselves, then that's going to change. We should, though, see an increasing and decreasing pattern again in our coefficients. Let's see if we do. Okay, we know we're going to have a subtraction sign. All right, so now we have a 4. 3 to the 3rd power is 27. And then, of course, we'd have x cubed. And we'd have y to the 1st. So 4 times 27 is 108. And we would have x cubed y to the 1st, which adds up to 4. I think we're in good shape. Plus sign. Now we have a 6. 3 squared is 9. X squared. And then y squared. 6 times 9 is going to be 54. Notice we're already decreasing again on our leading coefficients. And we have x squared, y squared. The squares add up to 4. We're going to have a subtraction sign. We have a 4. We have 3x and y cubed. Well, 4 times 3 is 12. X, y cubed. And then finally, plus 3x to the 0 becomes a 1. That's 1 times x to the 4th. So I'm sorry, y to the 4th. So we have y to the 4th. That is our binomial expansion. I want you to contemplate for just a minute what it would be like if we had to multiply this all out. 3x minus y, 3x minus y, 3x minus y, 3x minus y. If we had to multiply all that together, and how much time and so many places for error, that this is such a time saver. Just like our original binomial shortcut was, this is the shortcut for binomial expansion I think this saves you a lot of time. Hopefully you do too. Go Bearcats. Let's take a look at one more thing. All right, almost done. Go Bearcats. All right, the last thing we're going to do is we're going to find a specific term in a binomial expansion. In other words, if we have a really large expansion, let's say we have something to the power of 9, then there would actually be 10 terms written out there. And let's say we wanted to find just what that fifth term was, what that term was. What if we wanted to know that term? All right, so let's take a look at what the formula would look like. Again, I would write this in my notes. Matter of fact, I want to see this highlighted in your notes. When I look again, this is another thing I want to see highlighted. All right, so I want you to look that you would still be using your coefficient is in R, and that's how we can generate the coefficient of a particular term. Then we would take the first term of our binomial, that's our x term, and we would raise it to the n minus r power. We're going to take a look at why that is in a minute. And we would take the y term and raise it to the r power, and that will give us our coefficient, our term value in the whole thing. So remember, n minus r is the power minus the r, but remember our terms all start with 0, start at 0. So let's take a look at this by example. Please write this down. I think this will really help you to know this. So we're going to start with this example, or we're going to go over this example. Let's say we have a plus 2b to the 8th power. And I want the 6th term. Find the 6th term. All right. Well, finding the 6th term then really is the 5th term on our row, because our rows start with 0. So if it's 0, 1, 2, 3, 4, 5, and if it's the power of 8, we would have 6, 7, 8. But if you count from 0, that's 9 terms. We want to find the 6th term. So we want to find 1, 2, 3, 4, 5, 6. Where really, our R value is really 5. Our R value is really 5. And that's just a little tricky. You just have to know that and think about that pattern and remember that it starts at 0. So here's what we would do. We would find our coefficient by C8, 5. Okay. Then we would take our first term. This is using this information right here. We just did this. Take our first term, which happens to be A, and we would raise it to the n minus r power. And we would take our second term, which happens to be 2b. That's our y term. Remember, this is our x and this is our y value now. Our 2b, and we would raise that to the r power. We'd raise that to the r power. And that would give us our term value. So let's do that. First of all, let's do the factorial here. So this is going to be 8 factorial. This is from your binomial theorem. It would be 8 minus 5 factorial, and then it would be 5 factorial. So that's one thing. Then we would have a, and n minus r would be 8 minus 5, or to the 3rd power. And then we would have 2b, and 2b would be to the r, which is the 5th power. Let's go ahead and do the math on this. So 8 factorial, 5 minus 8 is 3 factorial. So let's do 8 times 7 times 6 times 5 factorial over 3 factorial, 5 factorial. The 5s would cancel out. The 3 becomes 3 times 2 times 1. Remember, the 1 doesn't really make a difference for us. 2 goes into 8 4 times. 3 goes into 6 2 times. Okay, so that's going to get us 4 times 2, which is 8 at the top. 4 times 2 times 7. So we're going to have 4 times 7. And 4 times 7 is 28. And 28. And 4 times 7 times 2. So it would be 28. 28 times 2 is 56. Okay, so that's the binomial in the front, or the coefficient in the front. Now we would have a cubed, And then be careful, we have 2 to the 5th power and b to the 5th power. So 2 to the 5th power would be 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So we'd have 32 b to the 5th. And finally, we would have to multiply 56 times 32. Okay, and we multiply 56 times 32, which is 1792. That sounds like a history date. Sorry. Okay, a cubed and b to the 5th. Let's just double check a couple of things. 3 and 5 do add up to 8, so I think we're good right there since the original was the 8th power. That's just a small little quick check to kind of notice in case you make a careless mistake. All right, there's our answer, and that's how we would find a specific term. All right, I will see you tomorrow in class. In class tomorrow, be prepared with your notes. Make sure you've highlighted the things I've asked you to highlight, and you may use your notes in class tomorrow for our practice. We will be practicing. We'll have, each of your groups will be a team. You'll have some questions to answer and then trade with other groups so that you can get all the questions by the end of the period. All right, have a good evening and go Bearcats!